to speak at this colloquium. So I will talk about my work on terrestrial gravity fluctuations as fundamental sensitivity limit of gravitational wave detectors. It's not, not only my work. We have many people working on this topic today. It is something, that we didn't have to worry too much about in the past, but it's becoming the more we push to lower frequencies with our detector sensitivity, the more important it will get. Before starting, I want to make a comment about what I mean really by fundamental limit, because it's not something that I think of as something that we cannot overcome, but it is a kind of a limit that is very hard to overcome. Let's say you have to really scratch your head for a long time, work on a method and do some R&D for a couple of years to really understand how to possibly solve the issue and overcome this limit. So in that sense, it's something that that you cannot just solve with gradual detector improvement, but you really need a new approach. And this is what's needed if you want to do something against terrestrial gravity fluctuations as a noise in your detector, for example. Then you really have to come up with a new idea and see how it can be solved. Okay, so. So far, let's say we have current infrastructure. This includes at the moment Virgo detector, then the two Ligo detectors, the Kagra detector in Japan, which is underground. And then we are going to have very soon another detector, well, very soon means maybe in a couple of years, another detector in India. And with that infrastructure and the upgrade plans that we have at the moment that we foresee for the next couple of years, we believe that we can achieve a certain horizon distance for binary black hole detections, which is at about redshift z equals 2. Now that's already that's far, that's good, but in fact it turns out if you really want to open up a very rich science case in terms of cosmology, in terms of detailed understanding of the waveforms, and that means maybe testing GR, maybe understanding the internal structure of neutron stars and so on, then you need something better. And you cannot realize this with the current infrastructure. So you really need something new. And that would be called Einstein Telescope for Europe and Cosmic Explorer for the US. So that I will explain a little bit more what this is, but Einstein Telescope is conceived as an underground detector and Cosmic Explorer as a surface detector, both much larger infrastructures than what we currently have with Ligo and Virgo, for example. Now, with that infrastructure, we believe, and for the first realizations of detectors in these infrastructures, we believe that we might get to a redshift of z equals 100 with our most distant detections. And that is well in the dark ages of the universe. So that really opens up a huge new science case that we cannot cover with the current detectors. Now, for the z equals 2, we might really not have to worry too much about gravity, about gravity gradient noise, which I prefer to call Newtonian noise, or terrestrial gravity noise. So that is, this is because the current infrastructure will not allow you to make observations, let's say, well below 10 hertz, or maybe you will not even get to 10 hertz really with good sensitivity. So that means you're kind of avoiding the gravity noise problem in these detectors. But it plays already a huge role for the next generation infrastructure. And this, so even though we don't yet build these detectors, because it's important already for the planning, Einstein Telescope, the main motivation to propose it as an underground detector is in fact the gravitational noise from the atmosphere, most of all, but also because of the seismically driven gravitational noise. So that has led, above all, to that decision to propose it underground. There are other benefits which are not that important, I would say. So that is the story. So it's really a major issue for the future, and generally connected to the problem of pushing the observation band to lower and lower frequencies here on Earth. Okay, So just to summarize quickly before we go go over to environmental noise. So what a couple of things you have to do if you want to go from this Redshift 2 infrastructure to the next generation Z = 100 infrastructure. So you make your detectors longer. That's true for Einstein Telescope and Cosmic Explorer. Einstein Telescope also you make you underground, as I said. There will be we plan to use higher laser power. In the arm cavities, we want to improve our quantum technologies, the performance of the squeezed lights system. Then we will have to implement cryogenics, and that might bring some of our test masses to maybe 20 Kelvin, maybe lower. We will see about the details. Then we have to reduce the coupling to the environment, and this is true essentially for all environmental influences. Ground vibrations, magnetic fields, and in the end, even though for example, the Einstein Telescope is foreseen to be underground, which is a gravitationally much quieter environment than the surface, still it depends on the site whether we need a further mitigation of gravitational noise, and we call a possible method to achieve that is the Newtonian noise cancellation. And so I'm going to talk about this as well. All right. So now a little bit about the role of environmental noise. The by far most important measure that we have to decouple the interferometer from the environment is the vacuum system, of course. So that is absolutely essential. We cannot have essentially any of the components of the suspension system, of the test masses, or the laser itself have contact to air, so at least not in the most sensitive part of the experiment. And there can, of course, be concerning the laser. It can be scattered, but even if that were not an issue, of course, any atmospheric perturbation would directly couple to a laser propagating inside of it. So it's absolutely, for many, many, many reasons, essential to have all of this in vacuum. And it's also the most important component of the detector, really, to when you construct it, of course. So at Virgo, that's how it looks like with the long tubes and the towers that you have and the buildings which host the suspension systems and seismic isolation systems. Now, the other important part is, the next important part, I would say, is the seismic isolation system. In Virgo, it takes the form of what we call a super attenuator, which I believe to the right, you can see this, is probably around 6 meters tall, quite tall compared to, for example, the more compact system that Ligo realized. And it is a sequence of pendula, essentially, and other components to achieve, in all degrees of freedom, essentially, a seismic isolation above some frequency. And so essentially to the left, you can see how this one is supposed to perform. Not that we are really able to, currently at least, to measure this in the detector, the performance, because we don't have the sensitivity yet to directly observe maybe limitations from that. But what we predict with our models is that, for example, the purple curve here is for the super attenuator for Virgo. And you can see that a couple of hertz, like at 4 hertz, it's supposed to already suppress ground motion by 12 orders of magnitude. Okay, so that's huge. And in fact, I mean, why we have no guarantee that it actually performs that well now inside the interferometer, assuming that this is so. What did I want to say? It's actually overperforming. So this is much better than we currently need for Virgo. This is, by the way, also a reason why maybe in the Virgo community we are slightly more optimistic to be able to push to lower frequencies with the current infrastructure already compared to LIGO. So the LIGO seismic isolation was much more designed to meet the requirements for a certain target. And the super attenuator in Virgo is more like designed as a, with a lot of margin in principle, assuming that this is really the achieved performance. And nonetheless, a modification of this is currently foreseen also to be used in ET, but these details might certainly change still. So another thing that I want to give as an example is magnetic noise. Another thing that we don't worry too much about right now. Magnetic fluctuations of the environment, and most of that is again produced really by the infrastructure, the electronics that you have around the detector. So this magnetic noise is, people have tried to estimate how much it contributes to current instrument noise. And so in the lower left plot, you can essentially see the result of these analyses. There are some Virgo sensitivity curves during the second and third, O2 and O3. The gray band is some magnetic noise projection that is obtained by essentially measuring the coupling of magnetic fields to the detector with coils. The circles here are obtained by doing noise injections. That means you're operating the detector, and then again a coil would produce some signal at some frequency, and you would measure how it pops up in your interferometer data, this injection, and then you would use it to scale essentially the influence of the actual ambient field of the ambient magnetic field to make noise predictions. So all of these circles and also the gray band, so all of these noise projections that were done in the past for Virgo show that it's currently not an issue. It's well below other noise at the moment, but this might actually change. In any case, this noise is going to be really important again for Einstein telescope, something that we have to deal with, I think, already by design to improve our concept of the payload or wherever the coupling really happens. Something else that I just want to point out quickly about the magnetic noise, there's an interesting aspect of it. So while we are at the moment dominated really by, let's say, electronics producing magnetic fluctuations, there is also a natural background of magnetic fluctuations. And at these low frequencies, these are associated with what we call Schumann resonances. And these are essentially waves that are wrapped around the globe, guided by the atmosphere. And so they are, of course, of the finite diameter or circumference of Earth. There are certain resonance frequencies associated with these waves, and these are forming then the Schumann resonances, that we see, for example, in the spectrum to the upper right. So that we cannot get rid of. This is present everywhere on Earth, and it's the interesting aspect is that it's coherent across very big distances. That means if you measure here, for example, in Italy in my office, and then, well, my office has for sure other noise dominating, but let's say at a remote location in Italy and at a remote location in Japan, you make these measurements, then you would see a very strong correlation between them. And this is clear just because this is associated with a global wave, right, which is wrapping around the Earth. So, and that might, for that reason, create correlated noise in different gravitational wave detectors if there's significant magnetic coupling. And that's an issue that in principle we know how to deal with, but something that we didn't have to worry about much so far, but which will also be an interesting feature to think about in the future. Okay, so now let's go over to Newtonian noise. So there, anything that perturbs the density in the environment is leading to some kind of gravity perturbation at the test mass, shaking it, randomly typically. These can be moving objects, but for the detectors, for gravitational wave detectors, of course, during an observation run, during the science mode, if you want, you will not let any person near the test masses walking there or any heavy structure moving around near the test masses. This is simply not happening during observations. So we don't have to worry about all of these things. What is left in the end, what we really worry about are the seismic field, the environmental fields, including the seismic field, the acoustic field, temperature and humidity fields, can all be potentially important sources of Newtonian noise. Now, in the following, I will mostly focus on the seismic field, just to say that in reality, it's almost the atmospheric Newtonian noise from acoustic fields especially, that let's say that makes it necessary to go underground. But in the end, you can get rid of it very quickly by just going, let's say, 100 meters underground. So we are not really thinking much about the atmospheric Newtonian noise anymore. When, for example, thinking about Einstein telescope, we are just assuming, okay, a few hundred meters underground, it will not really be an issue anymore, at least the atmospheric component of it. So we don't have to think about canceling it any further or something like this. So the detailed understanding that we are developing of Newtonian noise cancellation revolves around the seismic Newtonian noise, simply because we might still be forced to do some cancellation of it. Okay, so there are many different contributions. As I said, very quickly, just this is like from 2012, a Newtonian noise budget that we produced for LIGO. There is some, the blue curve is some LIGO target that was proposed at that time for some upgrade that could be done with the LIGO detectors. So I don't think that this is still up to date, this sensitivity target, but you can see a couple of curves that we produced here from the seismic field, but also there were strongly vibrating wall panels that we thought might produce Newtonian noise. The building itself with its metal and concrete structure is vibrating. Then there are vibrating fans for the part of the ventilation system, and also the sound field inside the LIGO buildings were considered, and all of these sources were producing a Newtonian noise spectrum that we added here to this budget. So in reality, you might want to consider a few things, but it turns out that the seismic field at the LIGO site at least produces by far the strongest contribution to Newtonian noise. That was one of the insights that we got. And this is still more or less the story also for Virgo, which has different site properties, but it's still we still come to the same conclusion for the Virgo site as well. Okay, so just briefly about the sources of seismic fields. This is how you start, because site selection and understanding your site is really crucial as a starting point, detailed understanding before you do any site selection, for example. So there are natural sources which are mostly known at lower frequencies below the detection band. For example, between 0.1 hertz in the upper left figure, in the there's a seismic spectrum. There's a histogram of many seismic spectra collected throughout the entire month of March at LIGO Livingston. And so between 0.1 and 1 hertz, you have this huge peak, which we call oceanic secondary microseismic peak. And there's a secondary peak at slightly lower frequencies. So this is from the ocean waves. Then already at a few hertz at this site, at least during the summer months, you have human-made sources. Between about June and September, Livingston has some excess noise at a few hertz. Coming from wood logging. So that detector is located in the forest, if you want, and then in the summer months, they are logging the trees, and that is producing excess noise for some time. And that, by the way, had some impact on the planning of that detector early on, but I think I believe it's not a major issue anymore, this excess noise. But nonetheless, these are the features that, of course, that you want to understand about a site before you go there. And that feature in this example, by the way, was discovered only later, not during site characterization, because they never surveyed the site for a whole year. Of course, with the Einstein telescope, we are much more careful about this. We do make site characterization for a couple of years, 1 or 2 at least, to really understand the properties and the variations with time. Now, interestingly, in the middle plot, there are 2 spectra that we compare. So above 10 hertz, it turns out that the seismic noise that dominates the spectrum is produced by infrastructural sources. That includes the ventilation system, pumps, and other, chillers, for example, and things that are required to let's say stabilize temperature in the laboratory buildings, and so on and so forth. There's this very nice analysis that people were able to do because there was a power outage, essentially switching off all these infrastructural noisemakers, but keeping the detector running. I assume that there was some UPS that kept the detector running. I don't know the details of how this all happened, but in any case, what you can see is that if these machines are all off, then the seismic noise at the site above 10 hertz is about a factor 10 almost weaker than when all these machines are switched on during regular operation. So what you can say is essentially that the infrastructure was not really well designed. So that one could do better. One can for sure avoid this excess noise. And this in the next infrastructure for sure is a crucial point to make sure that we do not introduce any excess noise in the Newtonian noise band from our infrastructure itself, by our infrastructure. And a good example is Cagra. So Cagra realized to the right, you can see that there's a seismic spectrum again. If you compare the Cagra spectrum with the Ligo Livingston spectra, so it's the same units. So it's about more than two, at some frequencies, more than 2 orders of magnitude quieter at a few hertz, or around 10 hertz than the Ligo Livingston side. And this is already with all the infrastructure running. Now, this spectrum only goes to 20 hertz, but at least up to 20 hertz, there's no significant excess noise that the infrastructure produces underground, which I think is a miracle, essentially, because given how quiet that site is, because of course that they also have pumps and ventilation system. However, if you extend that plot to, let's say, 100 hertz, it would look different. There's a huge excess noise around 50 hertz, probably rated to some machines. I don't know exactly the source, but this is not so relevant for Newtonian noise. But imagine that the infrastructure had caused at the Cagra side excess noise, around 10 hertz. It would be it would have been a huge error because of spending a lot of money to go underground to realize an underground detector, which really costs a lot, and then forfeiting all of your benefit by creating a noisy infrastructure. So they somehow avoided that failure, which is good. So, and this also tells us there's a good chance that we can achieve the same with Einstein telescope. Okay, so now I should say, what we know so far is, okay, you should pick a quiet site. Underground is perfect. There are also quiet sites at the surface, not so much in Europe, but in some other continents, you can also find relatively quiet surface sites. However, as I said, the atmosphere is something that you have to be worried as well about. So even if you pick a really seismically very quiet site, it might still be that the atmospheric Newtonian noise would become a limiting contribution. Now, you also don't want to create noisy infrastructure, fine. Now, in the past, maybe 10 years ago, we thought this is enough, essentially, to make sure that for Einstein telescope, we do not have to do any Newtonian noise cancellation. Additional mitigation scheme that I'm going to explain now. It turns out, though, it's not really true. It depends still on the site. So there can be underground sites which are just a little bit too noisy to avoid Newtonian noise cancellation. Now, let me give you, explain that idea to you with the example of Virgo. So for Virgo, I said that at Virgo we have more the optimism, let's say, to be able to push maybe to a little bit lower frequencies with the observation. Not sure if that really means that Virgo will succeed to beat LIGO ever at low frequencies, but let's say we are, maybe because of the super attenuator, we believe that we might get to slightly lower frequencies. So for that reason, we have started also to develop a Newtonian noise cancellation system, which is not really part of the LIGO design for the next science run. So what we have done is to deploy seismic arrays inside the buildings. And what will be done is now, so in the end, these will be about 120 seismometers, inside the buildings. And so we will take the time series of all of these seismometers and let them go through a magic linear box. So there's some kind of linear filter that will filter the data and add it all up to produce one output time series. And this output time series will be the Newtonian noise estimate. And that estimate is going to be subtracted from the noisy, from the gravitational wave data, with a goal to make it less noisy, okay, to get rid of the dominant Newtonian noise at low frequencies. There are two questions. First, what is this magic linear box? And there are different answers to it, what it could be. I will explain this later. And also another question is, okay, you have all of these sensors, but where do you have to put them really? How do you first of all know that they should only be inside the building? Then shouldn't they cluster around some point, maybe closer to the test mass instead of being equally distributed and all of that? These are important questions. I'm explaining this a little bit more now on this slide. So this is a complicated slide. I have to go through this carefully. So essentially, this is explaining to you the optimal way to design a Newtonian noise cancellation system. And we have all the pieces together now to do this, but it's a little bit a complex procedure. So separate from the main issue of designing a Newtonian noise cancellation system is the filter choice. So the choice of noise cancellation filter, which is here in the red box, this is a separate problem that you can address whenever you want. It is not related to the rest. So the rest is about the sensor placement, the optimal sensor placement. So then, you know, when we first talked about this for Virgo, people said, well, you know, we are a rich group. We can give you like, you know, 2 million euros and you buy as many seismometers as you like. You deploy them all over. And then why do you care about seismometer placement? You will just, monitor every square meter that you have in the rooms. So in principle, yes, that sounds like a good idea. In reality, it's not. So it turns out you can never do noise cancellation with so many sensors. And there's a fundamental problem that you cannot overcome, which is about the filter, the optimal filter that takes the input, that takes all the seismic data as input and provides an internal noise estimate. This filter somehow needs to be calculated. It's not something that you can model or something. It is something that you need to calculate from data. And it turns out that the more sensors you use, the larger gets the error on the estimate of that filter. And so this statistical estimation error of the optimal filter will kill you when you have too many sensors. And it will be the limiting noise contribution and limit your performance of noise cancellation. So this is why using many sensors is a bad idea. In fact, you should use as few sensors as possible. Then it's just really the problem then is, where do you put these sensors? Okay, so this is why the optimal placement is such an important question. By the way, for ET, which is an underground detector, if you want to place many sensors underground, this is just prohibitively expensive. So for example, placing a few hundred sensors underground in boreholes will cost you, a few $100 million. Because it is like, well, a few $100 million, yes, basically, or 100 million or something like this. So it's because it's really expensive to make a borehole for seismic installation. Okay, it's not like a cheap borehole that you make for a geological survey. These boreholes for seismometers are really expensive. So you do not want to make too many of them. For that reason, again, economy is important and you want to optimize the placement of these boreholes. So this story should then explain, okay, let's make a site survey. Let's put as many seismic sensors, at least temporarily, at a site to make measurements. And what we are mostly interested in is correlations between seismometers. I will explain this better also later. So then make correlation measures between many seismometers that you place, and then make also a few boreholes, measure underground and so on. So you have a huge number of correlations. Still, as I said, underground, you will not have too many surveys, even in preparation for a site, because it's just too costly. So what do you do then? So your knowledge of the seismic field is incomplete. It always will be. Now, can you do something about this? Yes. So there's a way that you can do a Bayesian array optimization. What you can do is you combine your observations with numerical simulations and Newtonian noise modeling. So you can make finite element simulations of seismic correlations. In these simulations, you would not put any properties of the seismic field, but instead you would include something like topography, geology, and based on this alone, you would make a seismic simulation and you would get simulated correlations between any 2 points in your region. And now this you can combine in a Bayesian way. So this would provide a prior to a surrogate model, and then you can use the data, the actual observations to give you a likelihood. And then this together, the likelihood from the observations and then the prior from the simulation, you can combine to a Bayesian surrogate model of the seismic field and it's gravity perturbations. And this allows you, the surrogate model allows you now to predict essentially the performance of a Vena filter and the noise cancellation for arbitrary numbers of seismometers that you place anywhere in the field, and wherever they are located. Okay, so that's the optimal way. And this is how we actually design for Virgo right now, the system. We have done exactly this. Of course, we don't need to go underground with the measurements, but we have done exactly this scheme for Virgo to come up with the final configuration of the arrays that we are deploying now for the Newtonian noise cancellation system. So to illustrate this a little bit further, the process for Virgo, we deployed for a site characterization, a seismic array. So these were at that time 40 seismometers here in the shown for one of the end buildings. We leave them, we just need a week of data, essentially, something like this. In reality, this array was there for a whole year. But then with that data, this is kind of the data that then you have cross correlations between all of these sensors, and this provides you the likelihood. And then you can get, you come up with priors from some numerical simulation or modeling, Newtonian noise modeling of correlations. And this together, you put then into a Bayesian optimization scheme, which is based, in our case, we have done this with Gaussian process regression. And then you come up with such heat maps which tell you where to place seismometers. You can even predict, depending on the number, on the upper right plot, you can predict also the performance of the system in the end, where a value of 1 in this performance measure would mean that you can subtract all of the Newtonian noise. And so 0.5, so this is noise power, so 0.5 would here mean half of the Newtonian noise power you can subtract. So, 15, around 15 seismometers per test mass is a good number. That's something that you need to do good noise cancellation if you have the seismometers placed optimally. And based on all of this, we came up with the final array configuration for the Virgo end buildings, as you can see in the lower right plot. This is then the product of the optimization algorithm that we are running with this Bayesian optimization scheme. And so this is how it currently looks like. This array, this array is deployed at the 2 end buildings at Virgo. So now let me come back to this filter, this magic linear box. So the filter needs to be implemented in time domain. It needs to be causal. So because we want to clean up data in real time without artifacts. So that means the way we represent this filter is like a finite impulse response filter. So this is just a filter that, let's say, has a couple of coefficients. In reality, per channel, it has maybe around a few hundred to a few thousand coefficients that you apply to time series. You multiply samples of a time series with these coefficients, and then you add up all of that and to produce an output sample. Now, in this equation here, the Vena filter coefficients are here this vector h. Then on the right-hand side, you have another vector, which is consisting of the correlations between seismometer data and gravitational wave data. And on the left-hand side, you have a huge matrix, which is the correlation between all of the seismometers. Now, this matrix can have a few million coefficients. Because you have 100 sensors, let's say, and for each sensor, you have a few thousand, maybe, coefficients. So if you then take all the cross correlations between all of these, then you can get millions of coefficients, and that's the problem. Now, this Vena filter coefficient is calculated by matrix inversion. So the matrix on the left-hand side of the cross correlations between all the seismometers must be inverted, multiplied with the vector on the right-hand side, and that result gives you the Vena filter coefficients. So millions of coefficients, which are millions of estimated correlations between seismometers, go into the calculation of a finite impulse response, a Vena filter. And that's the reason why it doesn't work so well, typically, because you have a huge statistical error estimate in the end accumulating into the coefficients h of the Vena filter. And so you cannot do this. We will not do this. We will not use Vena filters in Virgo. It's just too limiting for us. You can say, but okay, these are all correlations. So one way to reduce the statistical error in a correlation estimate is just to increase the correlation time. So why, instead of using an hour of correlation time, why don't you take a year of correlation time? So first of all, I think even a year would not be enough to reduce the statistical errors sufficiently. But even if it did, you cannot correlate for a year because seismic fields are not stationary. What this means is you have to update the Vena filter regularly to adapt to drifts in the field, changes in the seismic sources, so you do not have infinite amount of correlation time. So you end up with a certain level of statistical error that you cannot overcome fundamentally because of the non-stationarity of the seismic field. So what else can you do? There are other linear filters like the Kalman filter, which is really not strictly not really linear, but you can even do something else. You can, these coefficients H of a finite impulse response filter, you can not only calculate as a Vena filter, but also by gradient descent. So essentially, you have a gradient descent algorithm that finds the optimum values of these FIR filter coefficients to reduce the noise. So this is not ad hoc anymore based on correlations between sensors, but this is really coming out of a gradient descent, much like you would, for example, train a neural network when you do machine learning. You're using gradient descent to find optimal weights of your neural network. Here you find the optimal FIR filter coefficients with the same method. And this works, as I'm going to show you. In reality, you could also work with a nonlinear filter if you wanted to, but effectively, all of these filters have to be linear. Even the ones that start as a nonlinear filter, they have to be linear because otherwise you will not be able to do any good noise cancellation. So here, some demonstration of the difference between a Vena filter and the gradient descent. So here, this is a test of noise cancellation on a seismometer. So here you can imagine that what we did was we had an array of seismometers, and one seismometer we picked as a target. And so that seismometer had a certain spectrum, which is here shown in blue, the original spectrum of that seismometer. Now, all the other seismometers that were in the array were used as input to a filter to do then the cancellation of the seismic signal in the target seismometer. So when you do this with a FIR Vena filter, then you get as a residual after subtraction this orange spectrum. And what you can see is now this ANN residual, artificial neural network, and that's a bit of a misnomer. In reality, it's a linear filter that I'm applying there with the same number of FIR coefficients as the Vena filter. Okay, so these two filters are, identical except for how you calculate the coefficients of the filter. And and you can see that with gradient descent, that's how you calculate this filter here. The green residual spectrum is below the Vena filter. So despite the rumor that the Vena filters are said to be the optimal linear filters for cancellation of stationary noise, this is not true, because in reality, there are always some constraints about statistical errors, about correlation times, and so on and so forth. So then you have to come up with, you can come up with a better method to do the filter calculation. Okay. Now, the last thing, more complicated than I'm going to show. It's not getting more complicated than this. I hope you're still with me. So here is something that we were also able to do already now. This is a Ligo Hanford Newtonian noise experiment. Let me call it this way. So during the second science run, we knew, of course, that the noise at low frequencies at that time was still way higher than what we expect the Newtonian noise to be at LIGO. However, we also knew that if we just have enough correlation time between seismic data and the gravitational wave data, then maybe we will find correlations at some point. These are very weak correlations, but just with enough correlation time, you might find them in your data. And so what we had is an array, as shown in the upper right, an array of around 30 seismometers where inside the corner station of the Ligo Hanford building, also for a year about. So we used a couple of months of data for the study, essentially correlating now data for a couple of months, using these correlations to calculate a Vena filter. We had to do this in time in frequency domain because in time domain, we would be forced to do this with an FIR Wiener filter, and there are too many coefficients. So the statistical error would be lousy. We cannot do it with an FIR filter. But here, just because we wanted to look at the spectrum, it was fine to do it in frequency domain. In frequency domain, the Wiener filter depends on way less filter coefficients because there's no correlation between different frequencies. That's crucial. So in frequency domain, you can neglect correlations between different frequencies because we assume the field over long averaging times, over very long averaging times at least, to be stationary in the Newtonian noise band. So that means like the correlations between different frequencies should be negligible. So then under this assumption, there are way fewer correlation estimates that you need to calculate the Wiener filter in frequency domain. And then you can reduce a lot the statistical error, which allows you to really dig into the noise. That's what we did. And now the interesting curve is the red one, which was the original Ligo's gravitational strain noise spectrum at that time. I mean, also during O2, Ligo Hanford got better than this. Then there is the purple spectrum, which is interesting, and the solid black line. So the solid black line is the statistical error that we estimate to have from all the correlation estimates of our frequency domain Wiener filter. Now, whenever this purple line, the purple line is the noise inside the Ligo detector, which is correlated with ground motion. So in reality, what we do is we calculate a Wiener filter, and the spectrum of the output of the Wiener filter is the purple curve, okay? And it's the noise that is correlated with ground motion inside the Ligo data. That's the same thing. It's a spectrum of the output of the Wiener filter. So, and whenever this purple curve lies well above the black solid one, we know that we have found something. So we know at these frequencies, for example, between 10 and 12 hertz, we know that there's some noise that we could subtract with a seismic array if we had to. At that time, we didn't do it because that noise was just like way below other noise. We didn't care. But this might be something that Ligo might want to do in the future, because the red curve today, well, at the end of O3 and maybe especially in the next upcoming science run, is probably going to be significantly lower, maybe an order of magnitude or more, who knows, compared to what you see there in this plot. And then you might want to have the ability to subtract some of this noise away. So, by the way, it doesn't really matter if this is Newtonian noise or something else. We don't know what the origin of that noise is, and it's very hard to find out whether this purple spectrum is due to gravitational coupling or some other coupling from ground to gravitational wave data. For example, it might be still some residual noise going through the suspension system, or it might be scattered light. So there are different ways ground motion can couple with the interferometer data. But whatever it is, we know that this noise, the blue spectrum, the purple spectrum, we would be able to subtract down to the red, to the solid, essentially to the solid black curve. Okay. So, okay, this is what we're getting ready for. Now, let me switch to ET. I'm not going through this precisely. So we have submitted now an S-ray proposal 2 months ago, essentially, or 3 months almost. So, we are hoping to have a decision about this next year. It should be next year. If there's a positive decision towards Einstein telescope, then we have a path laid out of technology development, construction, and all of that. Site selection, still a lot of site characterization that needs to be done. So all of that hopefully leading us to a first operation around 2035. That's the current plan. And as I indicated already, gravitational noise would play an important role. It already does, because it is driving mainly the decision to build, to propose ET as an underground infrastructure. Now, this is the Newtonian noise story simplified. Seismic Newtonian noise for ET. As I said, atmospheric Newtonian noise is kind of negligible I will come to that. There's one detail to take care of, but essentially, atmospheric Newtonian noise is negligible at a few hundred meters underground. So let's not talk about this anymore. On the left-hand side, you can see how Newtonian noise would look like from seismic fields if you build ET at the surface. So there are two contributions to the seismic field: surface waves and body waves. Body waves propagate freely in all directions of Earth. Surface waves are bound to the surface. The names are Rayleigh waves, love waves, whatever. So the Rayleigh waves are the ones, the surface waves that can produce Newtonian noise. And these surface waves would produce Newtonian noise that lies within this blue band. So orders of magnitude above the target that we have for ET, the sensitivity target. Now, even the body waves, if you are not at the very best side, underground side, even the body waves can limit you beyond what. So in a way that we cannot directly achieve the sensitivity target for ET. So for the not very best sides, you even have to think about these body waves, because on the right-hand side, what you can see is ET underground. What you see is going underground, all of this surface Newtonian noise is strongly suppressed. And if you are not at a really loud side, already at 300 meters, you get rid of almost all of the Newtonian noise from surface waves, okay? So that should be possible. However, the body wave Newtonian noise doesn't change at all, because these waves are not in any way, that field doesn't change its amplitude significantly between surface and underground. These are waves that propagate in all directions. So essentially, underground, you have the same body wave Newtonian noise than at the surface. At the surface, it doesn't play a role because the surface Newtonian noise is so much stronger. Underground, it can become very well the dominant seismic Newtonian noise. And if you are not at the very best underground side, then you might still have to do Newtonian noise cancellation if, to achieve your sensitivity target. So how would this look like in ET? Now, this would be a very complicated problem to solve. I mean, in principle, we know how, but this is also a huge investment. So ET has 24 suspended test masses. Okay, that's a huge number. So Virgo has 4, and Ligo detectors have 4. So ET will have 24. Half of them couple significantly to gravitational fluctuations, because half of them are associated with low frequency interferometers. Okay, so we talk about 12 test masses. So they are all so far away from each other, on purpose, by the way, that Newtonian noise between them is at most weakly correlated. So that means essentially you would have to set up a cancellation system for each test mass. So 12 seismic arrays that you would have to deploy underground. So now we have a study that tells us you need several tens of seismometers per test mass to achieve even a factor 3 reduction of underground Newtonian noise. Now, why you can only achieve a factor 3 has to do with the nature of the body wave field, which consists of several different polarization of seismic waves, which makes this much harder than subtracting surface Newtonian noise. So it's the mix of seismic wave polarizations which really makes it a really tough problem. So you need, then that means you come to an insanely high in the end, let's say 500 seismometers that you need to deploy in boreholes. Each borehole a couple hundred kilo-euros, and with all of these instruments. So this is going to be a very expensive system, to say the least. Anyway, so this is what we would have to do. Of course, then you have to be very sure that the boreholes you make are at the right location. And so we come back to this problem of array optimization, something that we are currently developing for ET. We have applied this to Virgo as well already, as I told you. But essentially what we have to do now is, in the end, the observation of a site, that's a given. The site teams will provide us with some seismic data, some borehole data, some surface data. So there's not much we can do about it. But what we can work on very hard is on the numerical simulation that gives you the priors on the seismic correlations. And so this is what we have now demonstrated with the numerical simulation using the topography of the Sardinia candidate site. And you could also add geological information to that model. We have not done really geology in our first run. And then you would simulate with, we use SpecTime 3D, which is one of these seismic simulations. You would simulate the seismic simulation correlations, and then that would give you essentially the priors for the array optimization. You add to this whatever site data you get, and that will then provide you the optimal array design that you can come up with based on the data you have about the site, based on your understanding of the physics, as modeled by the numerical simulation. And so anyway, this is computationally very expensive, but I think the problem in principle we have addressed for ET as well. Just a note on the atmospheric Newtonian noise. I told you for ET it's not going to play a role. It's sufficiently suppressed. But there's one detail you have to take care of, which is the acoustic field inside the caverns that host the test masses. The sound level is probably going to be relatively high. So you might have an issue with that little volume of air and the acoustic field producing gravity fluctuations. And you might have to set up like a microphone array in a three-dimensional deployment in these caverns to cancel, if necessary, that Newtonian noise contribution. So it's a problem that you cannot completely neglect the acoustic Newtonian noise, just the atmospheric part. Okay. Then I'm already at the end of my presentation. Of course, if you really want to have a quiet environment, then you can leave Earth. So I make shameless publicity of an idea that we recently submitted to ESA for a European Länder call. So we know that the moon is a seismically extremely quiet place. By the way, there have been in this year, because of Artemis, because of the European Länder call, several ideas submitted as concepts for gravitational vectors on the moon. Of course, building something like Ligo on the moon seems to be, even for me, who I'm like a very optimistic scientist, this seems to be extremely optimistic even to me that we are ever able to do this. But there are other possibilities. Somebody said, okay, let's deploy long fibers, optical fibers. What we proposed was to use the moon as a gravitational wave detector. That idea is, by the way, very old. It predates LIGO idea. Weber already came up with that idea, and maybe somebody before him, that the moon would respond as an elastic body to gravitational waves at essentially in the millihertz band, and you would then be able to monitor with a simple seismometer these vibrations that are caused by the moon with a seismometer, and then essentially the seismometer would have the gravitational wave data. And the moon is predicted to be extremely quiet. We don't know how quiet it really is. The noise background has never been observed. The Apollo seismometers were extremely sensitive, but not sensitive enough to see any noise background. Of course, what they saw was there were moonquakes, meteoroid impacts from Apollo, but they were not really able to see the background, the stationary background, which is what really matters here for this concept. And it's predicted to be really low and mostly driven by meteoroid impacts. So the near future geophysical stations that will be deployed with Artemis, for example, or commercial landers will tell us much more about it. But we already know that at some frequencies, the moon is up to 3 orders of magnitude quieter than the Earth. And that's very encouraging. So essentially, that is crucial then to and of course, that not only removes the gravitational noise from the picture, but also the direct seismic perturbation in these measurements. And yes, so that was my outlook slide for the future, something else that we hopefully are going to do. And with this, I want to end my presentation. Thank you.
Thanks. Thank you very much, Jan. It was a wonderful talk, very exciting, outlook as well. From the audience, if you have any question for Jan, please unmute yourself and ask.
I think during the talk there was some comment by someone who is probably from gravitational wave community on these correlations in this magnetic. It's in the chat.
I think I cannot see the.
I can read the chat maybe. More recently, we have observed there are some frequencies, magnetic noise from instruments is actually limiting Virgo's sensitivity, or might in the near future, from Pamela Janssen.
Yes, I think exactly. Okay, good. Yes, you were involved in the measurements actually, I think, or in some of these. Yes, okay. Indeed, yes, we are producing, well, the site is producing a lot of, I mean, at some frequencies, magnetic noise. And so that might become relevant, for the Virgo detector now. So that's true. Yes. Thank you.
So Jan, I have one very the last slide about moon as the gravitational wave detector. Can you tell us a little bit more about it? What do we have to look at? And can you measure the size, everything? Yeah.
So let me say a bit more. So essentially, there's this graph here that shows you sensitivity curves. So there's a strain noise curve predicted for LISA, for the space antenna, and then in comparison, two different concepts of the lunar gravitational wave detector, where the concept really means the type of seismometer that you will use. And people have proposed in the past what I call here a cryomagnetic concept, essentially where you have levitated test mass with a superconducting system, and then achieve very high sensitivity. That's the idea, at least. Then there's the optomechanical concept where you have essentially mechanical suspension and then an optical readout. So the point is that. So when you look at the sensitivity curve here, you can see it has a peculiar structure for this lunar concept. It has like this narrowband features up to, let's say, 10 millihertz. And this is related to the eigenmodes, the normal modes of the moon. So we know, given its size, we don't really know a lot about the moon yet. I mean, we don't have a lot of detailed understanding of the moon, but it's enough to predict that probably around the millihertz, we will have the lowest quadrupole mode of the moon, the resonance frequency, and has a certain Q value. And so that gives you a certain resonant amplification of its response to gravitational waves. This is why at this frequency, you are getting quite sensitive. And then there's a spectrum of these normal modes, which is discrete up to some frequency. And then it turns into like, an overlapping forest of modes at higher frequencies, where it then becomes more broadband response. Now, in any case, so you can then observe gravitational waves or sources that excite essentially these normal modes in the millihertz band. That's the main idea. So, for example, a massive black hole would chirp across these frequencies, and in a well-defined temporal sequence would excite these quadrupolar normal modes, one after the other, towards high frequencies. And then given the temporal sequence, you would be able to say what the masses were, for example, of this massive black hole, things like that. At higher frequencies, if, we are not, I have to admit, we are not yet able to model the gravitational wave response of the moon, let's say above 0.1 hertz very well. It's it's a surprisingly a not yet fully understood problem that we have to still do better. But assuming that these sensitivities can be achieved, which really depends a lot on how the moon responds at higher frequencies, we could also see, for example, white dwarf inspirals and mergers, because we are potentially even more sensitive than the LISA detector above 0.1 hertz. So there you would make observations very similar to Ligo and Virgo. It's kind of becoming a broadband detector at these frequencies. But in any case, it's always a surface displacement that is produced by gravitational waves exciting vibrations of the moon. And of course, what you have to take into account is that also the test mass in certain coordinate systems, I mean, it's always depending on the choice of coordinate system, even the test mass of the seismometer responds to gravitational waves in some sense. Relative to the moon, at least. So, so all of this needs to be taken into account to really come up with the correct response of the whole system to gravitational waves. And this is, I think, but this is how, in principle, how it works. What you could, of course, also do is for the millihertz frequencies, you could have a seismometer at two antipodal locations on the moon, the gravitational wave signal will be the same, even in a stochastic sense. But any other excitations by seismic events would not be the same. And so cross-correlation between them could be used to dig deeper into the noise here. So there are different ways that you could really make this work. And it depends a lot also, of course, on how good you can make these seismometers, because they don't exist yet. I mean, we are like orders, 2-3 orders of magnitude away in sensitivity yet from these seismometers that we would need.
How many years do you think?
Well, we are planning 10 years of development now. It requires a seismic platform on Earth. So you have to create a very quiet place on Earth to operate these systems in a linear regime without ground tilt. So ground tilt is always an issue here on Earth when you want to characterize instruments. On the moon, it will not be an issue for this concept. But in any case, demonstrating the performance of these seismometers on Earth, you need to set up a complicated laboratory with vacuum system, seismic platform, and so on and so forth.
Okay, thank you very much. Thank you.
Yeah, Jan, could I ask you a question? For ET, I mean, there are, as you say, 12 masses, but they're kind of in pairs, aren't they? There's the kind of central mass and one end mass very close to each other in each situations. Can one use the same array to compensate the two masses that are close to each other?
So yes, so we currently foresee them. Actually, I think what we will do in the end is we will keep them sufficiently apart. The current plan is to have, I think, 400 meters distance between these two. Now, I think you might even take more if, for Newtonian noise reasons, you want to keep them separate. Because in reality, you want to keep them separate also to benefit fully from the null stream. I mean, you know what that means. So if you create correlated environmental noise in different detectors, then you would just not have the null stream working properly for you, because it would also suppress the environmental noise in that null stream. But in any case, the few hundred meters, I think, are already enough to reduce the correlation between the test masses so that it's essentially independent noise. I think that the arrays that you deploy for this pair of test masses might have some overlap in a region, but it would not be just one array that you deploy. It would be two arrays where you can maybe use a few of the sensors for both. Yeah.
So Jan, maybe I will ask you one like a more basic question for my understanding. So I understand that you are using this array of sensors, not too many in number, so that you can inverse the metric to find the appropriate filter. But these each of these individually are probably far less sensitive than the LIGO detector or the gravitational wave detector itself, right? And the sensitivity is only scaling as 1 by square root of the number of them. So somehow the noise is estimated at a worse error than the signal. So how do you manage from that to?
Yeah, so the point is that the Newtonian noise estimate that you obtain is really coming out of the information about the seismic displacement. So it's a very strong signal that you are actually monitoring, the ground displacement, which leads to a very weak noise in the detector. So that means in terms of sensitivity, the seismometers are, so the best commercial sensors are way better than what you actually need. You just have to be able to observe the ground motion with sufficient SNR. And that information is then passed through a filter that outputs a very weak Newtonian noise estimate that is part of your detector noise, and you subtract that. So essentially, it's really just in the scaling factor between the seismometer as input and the Newtonian noise output of this filter that makes the translation between something strong, which is ground motion, and something weak, which is the Newtonian noise.
Okay, no, that's very good. Yeah, thanks. And do you have any preference for the type of your ground noise sensors? Because you also said somehow earlier that the magnetic noise matters, and I did not really understand. So if your final detection in LIGO, I guess, is through photo detection, right? So is it the current or something else that gets affected?
No, I mean for the magnetic noise is generally a separate problem, I would say. By the way, if you in the end up with significant magnetic noise in your data, you can also attempt a noise cancellation with magnetometers. It's the same concept that you apply to gravitational noise. But let's go back to your initial question about the sensors that you would use for Newtonian noise cancellation. Of course, you don't want to introduce any noise with these sensors. Typically that should not be the case, but we actually had that problem now somehow with at Virgo, because we chose to digitize. What you can do is you can send the seismic data in an analog fashion to some central data acquisition system, have a preamp there, and then digitize it. But then you might be worried about a noise coupling into the cable that transport the signal, which was not good. Or you can have, like, inside the seismic sensor unit already a digitizer and preamp. And then this unit can actually produce noise that you have to be, in the design of these instruments, a bit careful. But generally, I don't think that they produce any significant perturbation of your system, so there shouldn't be any worry. However, there, of course, the sensors that you can use, for example, for Virgo, it's so loud, and it's the same for Ligo. The ground motion is so strong that even almost the cheapest geophones are sensitive enough to do the job for you. So, I mean, we could have gone with €300 per seismometer sensors to do the cancellation. In the end, we did something more complicated, which cost around €1,000 per unit. For ET, we would have to use the most expensive seismometers that there are, the broadband instruments essentially, or GS13. So we are talking about 10K and more for each seismometer. Borehole broadband sensors cost 50K. So these are then more expensive. But for Virgo, for any lab environment at the surface, you can typically go with very cheap sensors to do the cancellation for you in the end.
Okay. Thank you. And one main question now is because we were also realizing that to do any of our experiments, we have to probably go underground. So the body waves still remain, right? So do you have other than these boring holes, any other ideas for body waves, or are there places on Earth nearer to the mantle or something where the body waves are less deeper?
So the only place we know which has very peculiar, so you have to look for a geologically very, very peculiar place where essentially anywhere nearby there are no seismic sources, and somehow the seismic waves, because body waves can propagate through Earth from one end to the next without much attenuation, so they experience very little damping. So you can look for a geologically very peculiar place which has no sources there, and then essentially sorry, I have to switch off my phone. And essentially all the incoming waves being reflected off some geological features. And one place we know where this happens actually is in the South Pole in the ice. So we know that there are some borehole stations in ice which have extremely low seismic noise, simply because somehow there are no sources, at least during the summer, let's say. The weather is not too bad. And then the waves do not really manage to propagate into the ice mass. They are being reflected off it to some extent, creating very peculiar conditions and making really low noise environment.
Okay.
So, but otherwise, there's no way. You cannot escape it.
So measuring and cancelling should be the procedure one should try somehow.
Yeah. Fortunately, that's the way to go, I fear.
Has there been any studies in South Pole? I mean, has any other group such as BICEP or some other experiments have done already some studies, base studies about the seismic noises, or even the neutrino telescope, because it sends sensors quite deep inside under the ground?
Yeah, so I think there are some permanent seismic. I mean, I don't know if we have anything as part of the astrophysical experiments, but I know that certainly there are permanent seismometer installations on the South Pole, and the data is public. So there's this IRIS server that collects essentially from anywhere around the world seismic data, and you can access South Pole data and look at it. And it's it's mostly effective. What the very quiet conditions are achieved above a few hertz. So that's where you really see a very unusually quiet seismic environment. Below, it's yeah.
But it doesn't help if you go sub.
No, and I think that is quite impossible. And this I can explain you, because if you go to low frequencies, which is maybe what you are really interested in, then the problem is that the waves become so long that they kind of ignore any geological features, except for like the very rough structure, mantle, crust. So they become like 30 kilometers long, and they don't really care if there's like a kilometer cube block of ice. They are not really reacting to that kind of feature in the geology anymore. So this makes it. This, by the way, also means that the surface waves you cannot escape by going underground, because they are so long that going underground, there's essentially no reduction in seismic noise at all. But so measuring, for example, at 0.
It's a kind of like a free fall. So on top of this, what we are thinking is that imagine now your Einstein telescope, but you allow everything to have a free fall in a drop tower. If I put the sensors and everything, the entire experiment in a drop tower.
Yeah. So if you put, but this is the point. You have to put really everything, including the laser. Yeah. So if you can make something so sturdy, or maybe you just want to have one run, but no. In any case, if you can make it so sturdy to survive a fall somehow, or a mechanism that it can be caught smoothly, then this would of course be the solution. But yeah, so important is to have everything falling, including the whatever you need. For example, this was one of the early errors with the atom interferometers, that they were arguing with the free fall, but in the very early days it didn't include the seismic noise coupling through the laser into their system. No. So this is not extremely straightforward to do. But anyway,
this I agree. Even the refrigeration system has to freely fall within this.
Yeah,
I guess the kind of thing which LIGO does with combinations of springs and things, we probably have to do with really a free fall rather than combinations of springs.
Yeah, it's tough to of course, there's no simple mechanical filter anymore. Well, if it's not. I wouldn't rule it out. I mean, it's at least extremely challenging to provide a seismic isolation system for these frequencies with mechanical filters. You can, of course, do some active seismic isolation to reduce noise just by sensing of seismic motion and feedback. But all of that is really kind of challenging on Earth. I mean, it's. Yeah, I think a combination of different measures can work in the end. Very challenging in any case.
Okay. So we are nearly done with questions. So maybe one last question, but only if you have time.
Yes.
Is regarding the
yes.
Yeah, regarding the prior.
Yes.
So how much do you already input some non-geological information and stuff in the prior, or I mean,
yeah,
just with your sensors you're probably not getting enough information, right?
No, I mean, the seismic observations is for us what we, all of the seismic information, what comes out of seismometer data, that's something that we would say belongs to what we call likelihood in this scheme. What can go into the priors, in some sense, is the geology, the topography. What you could also put into this easily into the numerical simulation would be the distribution of sources. So if you know that seismic sources are more clustering around the region because there's a city like 20 kilometers away from you, then you could set up your numerical simulation in a way that you are taking care of that detail as well. But otherwise, there's no easy way or any way I know of to somehow improve easily your numerical model with the seismic data, because that is a very, very complicated process. And there's a lot of randomness that you have to get out of this. And so I think we cannot push this very far, including somehow seismic information into your numerical simulations. But something like source distribution, that is, I think, feasible. So if your site characterization is telling you, okay, most of the time the waves come from a certain direction, then this is something that you can certainly take care of in the simulation as well.
Okay. Okay. Thank you. Thank you so much for any other questions from anyone? Yeah, if not, maybe we can thank Jan once more. And Jan, please stay in touch. Maybe we have some discussion sometime as well. Yeah.
Absolutely. That sounds good. All right.